Hey everybody. Recall that in the previous section we dealt with exponential functions, and this is what the equation looked like, right? Our basic equation. And remember, a had to be greater than 0 and not equal to 1. The horizontal line test shows that exponential functions are 1 to 1. Okay, remember our graph of an exponential function. Shape look like this or like this. So they are 1 to 1. They pass that horizontal line test. So that means that the equation defining the inverse of a function is found by replacing x and y. Okay, so if this is our exponential function and we just interchange the x and y, we get this function. We call this a logarithm, okay, symbolized by the abbreviation log. And you read it log with base a of x. Don't say log a of x or log a anything, because later we're going to realize that in special situations, just like when we don't have to write an exponent that's a 1, when we don't have to write the index in our radical to 2, there's going to be a time when we don't have to write the a. It'll actually be understood to be a 10, and then we can just say log x. But if we say log a, right, that means the a should be right here. This is the base, okay? The number a is called the base, and x is called the argument. So log with base a. Also, if we say it correctly, it's going to help us with working these problems. Okay, so again, here's just another definition, okay, where a and x, both, the argument now also has to be positive. So a and x both have to be positive, and a still can't be -1, because remember, this is simply an exponent. All we've done is just interchanged our x and our y, right? So I can rewrite these in this exponential form. All right, and here's just some examples showing us how to go back and forth from the exponential form to the logarithmic form. So a couple of things. A logarithm is an exponent. If that word log, and this really confuses a lot of people when we get to the logarithm section, because, oh, I not only have a letter in my math, now I have a whole word. If you don't like that word, replace it with exponent in your head, right? The exponent that goes on 2 to give you 8 is 3, right? The exponent that goes on 1/2 to give you 16 is -4. Okay? So over here, I could say the exponent, aka log, that goes on 10, right, to give 1,000 is 5. The exponent is 5, and remember, the is where equal sign goes. Okay, so you can look at these and see how they've interchanged back and forth from the logarithmic form to the exponential form. And then here's another diagram helping us remember that. Remember, the y is the exponent and the a is the base. And remember, that's what we call the big number when it's written as an exponent. So if we read this log with base a, okay, that's the base. And a logarithm is an exponent. So whatever a logarithm equals to is going to be our exponent. So let's try ourselves interchanging those from logarithmic form to exponential form. So here's my base, log with base x, right? And a logarithm is an exponent, so this is my exponent. So the exponent that goes on x to give me 8/27 is 3. The exponent is 3, and this is your base. Okay, now actually this is asking me to solve the equation, not just change it to exponential form, but as you can see, the way we're going to solve logarithmic equations is change them to exponential form. Okay, so now previously, we've already solved these, so one thing I can do to solve this is just cube root both sides so that I get the x all by itself. So the cube root of 8 is 2, and the cube root of 27 is 3. It was an odd index, so I don't have to worry about anything, right? Okay, the base is 4. The exponent is 5/2. Okay, the exponent that goes on 4 to give x is 5/2. Okay, now this is already solved for x. I just have to simplify this. Remember what that that fractional exponent means. The 2 down here, the 5 up. So the square root of 4 is 2. 2 to the 5th is what, 32? Okay, the base is 49. Okay, a logarithm is an exponent, so the exponent is x. And that must mean my argument goes here. Okay, now remember, when I'm trying to solve an exponential equation, I've got to make the bases the same. And I noticed that they have a 7 in common, so I can make this 7 squared to the x. And this I can rewrite as 7 to the 1/3. Now an exponent raised to an exponent, you multiply. This is all from the previous section, right? Once the bases are the same, the exponents must be the same, so 2x must equal 1/3. Okay, let's either divide by 2, or to make your math a little bit easier, we can multiply by 1/2. So x equals 1/3 times 1/2, 1 times 1, 3 times 2, right? Or 1/2 divided by 2. 1/3 divided by 2. Okay, so to solve a logarithmic equation, remember right now we're back to equations, change it to its exponential form. To solve a logarithmic equation, change it to its exponential form. Okay, now let's talk about a logarithmic function, right? A logarithmic function. So that's where we have y equals log with base a of x instead of log with base a of x equaling a numeral. Okay, so we've got these restrictions. The base has to be positive. It cannot equal 1, and the argument also has to be positive. Okay, so they've given us a basic function of log with base 2, starting with just showing how you could graph it by doing the inverse of the exponential function. Remember, we talked about how to graph exponential functions last time, and we would plot these points. Well, what we were doing was -2, to +2, and we have these points. And so remember, inverse functions, the graphs are mirror images, reflections along that line y equals x. So if you imagine folding this over that line, it'll stay here. Also, inverses, you can interchange the x and y values. So if this graph has -1 1/2, your inverse function, your logarithm, is going to have 1/2 -1. If this graph has 0 1, your logarithm is going to have 1 0. If this graph has 1 2, your logarithm is going to have 2 1. Okay, so here's the shape of our logarithms. I'm going to add that to my list, by the way, this shape now. And this shape. This will correspond to when we have fractional exponents, right? Okay, here's some characteristics of the graph of a logarithm. Okay, notice, because it's the inverse, of an exponential function, remember on exponential functions, we said they always contain the points -1, 1 over a, 0, 1, 1a. Okay, so on a logarithm, your points that you always have, the basic ones that I'll always say are 0, 1, and 1, whatever your base is. Okay, notice the y-axis is a vertical asymptote. On an exponential graph, we had the x-axis is a horizontal asymptote. Okay, the domain is 0 to infinity and the range is -infinity to infinity. Remember on the exponential, it was just the opposite. The domain was -infinity to infinity and the range 0 to infinity. Okay, now this stays the same. If a is greater than 1, then your function is increasing. Okay, so it's going to look like this. And if a is a proper fraction, then it's decreasing, and it's going to look like this, which we're about to see those. All right, so graph each function. Okay, the first step, and you might want to write these steps down. The first step when I'm graphing a logarithmic function is change it to its exponential form. Change it to its, you might want to write first step, replace f of x with y, right? Replace f of x with y. And I do that every time I'm graphing, right? We've talked about that, so I can see my x and y, obviously. Okay, so log with base 1/2, that's your base. A logarithm is an exponent, so that's your exponent. Okay, and now you're really graphing an exponential, but what I have to remember is start plugging in your y values. Usually we would go in here and we'd say, okay, let's plug in -2 through 0. Okay, I've got to plug in my y value, because if I put a -2 in for x, what? How can I figure out what y is? I can't, right? So because it's the inverse, I'm going to do the opposite of what I did with an exponential function. I'm going to plug my y values in first. And then this, we're old hats at, right? Just let y be -2. So I know that a negative is the reciprocal. So that's 2 over 1 to the +2 or 4. Okay. 1/2 to the -1 is 2 over 1 to the +1. Anything to the 0 power is 1. 1/2 to the first is 1/2, and 1/2 squared is 1/4. And then I have my values. And I know my shape and characteristics of the graph, so I can just plot them. Okay? So when x is 4, y is 2. Okay? When x is 2, I'm sorry, y is -2. So when x is 4, y is -2. Come on. Okay? If we would have missed that sign like that, once we got our points drawn, we'd know, what? That doesn't fit my shape. Okay. When x is 2, y is -1. Okay. When x is 1, y is 0. When x is 1/2, y is 1. When x is 1/4, y is 2. Now notice our base is a proper fraction. And so this is what I was talking about. When you have a proper fraction, your shape actually looks like this, as opposed to this, right? It's decreasing. Okay? Let's try this one. First step when graphing a logarithm, change it to your exponential form. So 3 to the y equals x. Right? This is the base. This is the exponent. And then remember to fill in the y values. Okay, so if I put a -2 up here, 3 to the -2, negative exponents mean reciprocals, so that's 1/3 squared, or 1/9. 3 to the -1 means 1/3 to the +1, or 1/3. 3 to the 0, anything to the 0 power is 1. 3 to the 1, and 3 squared. Now, if x is 1/9, y is -2. Okay, if x is 1/3, y is -1. If x is 1, y is 0. If x is 3, y is 1. If x is 9, that's way out here, y is 2. So it's just like right there. Okay. And there's our basic shape of a logarithm with a base bigger than 1. Okay, notice the points that they both have 1, 0, and 3, 1, and 1/2, 1. Okay, so to graph a logarithm, replace the f of x with y, change it to its exponential form, and on your xy chart, plug the y values in. Okay, now, just like with exponential functions, to graph these things, we're going to use translations, right? So it's still the same steps. There's nothing different. Change the f of x to y. Okay. Put it in its exponential form. Right? This is the base. This is the exponent. Okay, so here's my argument. All right, but actually, I'm not going to do that. Change it to its exponential form, but then just do the basic one. Like I want to think of this as y equals log with base 2 of x. This is just going to be a translation. Right? And I don't want to write it like I just did, because that's going to mess me up unless I keep that x minus 1 in parentheses, and we normally wouldn't. So let's just graph the basic function, just like we do anytime we're doing a transformation, right? Just the basic function. So that would be 2 to the y equals x. Get those basic points. Those basic points are be really easy to do. If y is -2, this would be 1/2 to the +2, so 1/4. If y is -1, this would be 1/2 to the -1, 1/2 to the +1. If y is 0, this would be 1. If y is 1, it'll be 2. And if y is 2, it'll be 4. All right, so we should be able to get those values quickly and easily, just like with all of our graphs. So if I was just graphing it log with base 2, I would have 1/4 -2. I'm not graphing it, so I'm not putting points. 1/2 -1. There's the 1, 0 again. 2, 1, 4, 2. Okay, this would be my graph. But I'm actually graphing, right, log with base 2 of x minus 1. So it's going to be these same points, except move to the right one. When it's inside with the x, it does the opposite. So right one, right one, right one, right one, and right one. Now that makes my vertical asymptote x equals 1 instead of 0, right? Because I shifted that whole graph over 1. So try not to cross that line. Okay. Then let's try it with this one. What's the basic graph you're going to plot? Right. Y equals just log. Interesting. All right, what's happening? Okay. Y equals log with base 4 of x, right? So 4 to the y, all of this extra stuff I don't care about. 4 to the y equals x. That just means we have to remember to plug in our y values first. So 4 to the negative 2 is 1/4 to the positive 2. 4 to the negative 1 is 1/4 to the positive 1. 4 to the 0 is 1, and then we have 4 and 4 squared. Okay. So, basic points. If x is 1/16, y is -2. Very close here to the axis. If x is 1/4, y is -1. Then we have the point 1, 0, of course. And then 4, 1. And then way out here, 16, 2. All right, so I'm going to take every one of these points and I'm going to move it left 2 and up 1, right? Just doing our transformations. Left 2 and up 1. 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 And for the one way over here, still left 2 and up 1, it's still way over there, but it's on that. Again, try not to cross this as now your asymptote. Okay. All right, let's try this one. What are we going to actually graph first to get our basic shape? Just y equals log with base 3 of x, or 3 to the y equals x. So our basic points, 3 to the negative 2, reciprocal is 1/3 to the positive 2. 3 to the negative 1, reciprocal is 1/3 to the positive 1. Anything to the 0 power is 1, 3 to the 1, and 3 squared. I've got my basic points. So I can graph them. All right. When x is 1/9, y is -2. Okay, none of these had fractional exponents, so they're all increasing functions. When x is 1/3, y is -1. There's the 1, 0 again, and then 3, 1, and again 9 is off my graph. So I'm going to take every one of these points and do what with it? Right, move it down one. Just down one is all. Down one, down one, down one, down one. Then draw in our shape. Okay? Let me know if you have questions, need any help. Okay, here's some properties of logarithms. These come straight from our properties of exponents. So to help us remember what these are, think of our exponents. Okay, the product property. So the product property for exponents, if you are multiplying two exponential numbers with the same base, and so this goes along all of these, for this property to hold, they all have to have the same base, right? Just like with exponents, or you can't combine them. These are exponents. If they have different bases, you can't combine them. But if you had the same base, then you add the exponents. So our product property says if you're multiplying your argument, you can separate it into two individual logarithms by adding, because that's what, this is an exponent, this is an exponent. You're adding your exponents. The quotient property, think about what happens if you have two exponents with the same base that you're dividing. What do? You subtract the exponents. So subtract the logarithms, subtract the exponents. Logarithms are exponents. The power property, if you have an exponent raised to another exponent, what do to those exponents? You multiply them. So here you're going to multiply the exponent by the exponent, right? So this one's going to become really important to us in the next section, okay? It's going to let us bring those exponents down to the front. Okay, again, think about this, the logarithm of 1, okay? A to the 0 equals 1, so the logarithm of 1 is always going to be 0. Anytime you raise anything to the 0 power, it is 1, okay? And then this one's going to be important too, because the log, a base A logarithm of A, if we have the same thing here, right, if your base is the same and this is a base, these are the same, then the exponents have to be the same. So this exponent, whatever exponent is sitting here, right, this is going to go to, if this is a 2, if these bases are the same, these exponents are the same, right? So if my bases are the same, my exponents are the same. And then this one, this is a crazy one that we're just going to have to remember. It's basically the same. If my exponents are the same, even though this isn't an exponent, so it's a little tougher to explain, but these are the same. But if your bases are the same, you can basically just get rid of that log part. Same thing here. If these bases are the same, and it'll just drop that exponent down, right, to whatever the exponent is. So if my bases are the same here, I can think of that too. And so this is going to equal whatever is here. Okay. All right, so that's my properties. I need to know those. This one's a little obscure. You might be, all you'll be asked on this is, I mean, you might have a problem saying, you know, A to the log with base A of 7 equals what? And you'll just say 7. So we got to know that for a couple of problems, but these are the ones I really need to know to use in our future problems. Okay, so we're going to practice rewriting each expression, okay? So we're going to use those properties. Since this is a multiplication, right? What happens if you have exponents with the same base that are being multiplied? I can separate that with an addition. That's it. That's all that is. This one, because my argument's being divided, I can separate that with a subtraction. Now remember, do not forget to write what your base is, right? It's a different thing if there's not a number written right there. It means your base is 10, which we'll talk about, I think, next time probably. But, so you gotta write the base. Okay, now this one, because a logarithm is an exponent, anytime I'm working with logarithms, just like when I was working with exponents, I want to see what my exponent is. Okay, I want to see what my exponent is. And then I'm using that exponent property to bring this out front. Right? Okay, so just using those properties to rewrite my expressions into individual logarithms. Right? You might see the usefulness of this. Now I've just got the log with one number, right? Log with base 9 of one number. Okay, so practice using those properties. Okay, we're going to keep practicing them. Okay, so I want to see this as an exponent, log with base a, and this would be then m squared to the 1/3, right? Or I know that's 2/3. However you want to go about changing that, m to the 2/3. Okay, and now I have that property where I can bring the exponent down. 2/3 log with base a of m. Once my argument is one number, one variable, one letter, one number, one thing in here, right, then that's when I know I'm finished. Okay, so on this one, remember, fraction bars are as if there's invisible parentheses on the numerator and the denominator. So I can change this to log with base a of m n q minus log with base a of p squared t to the 4th. Okay, now these are all being multiplied, so I can separate them with addition. So that's log with base a of m plus log with base a of n plus log with base a of q. Now I can also separate these with addition, but be aware this whole thing is being subtracted, right? So really it's like this if I separate them with addition. Log with base a of p squared plus log with base a of t to the 4th. And now my next step is to get rid of those parentheses. So we have log with base a of m plus log with base a of n plus log with base a of q minus log with base a of p squared minus distributing log with base a of t to the 4th. Now this one's good. It's just an m, just an n, just a q, but this is not just a p and not just a t. So I use that property to bring those exponents out. So in the end I have log with base a of m, excuse me, plus log with base a of n plus log with base a of q minus, now bringing that exponent down, 2 log with base A of P, and bring this exponent down, so minus 4 log with base A of T. We really need to get good at these properties because we're going to use these next time to help us solve these logarithmic equations. All right. So something I want to point out then, really we can do these in a shortcut. Okay. Notice anything that's in the numerator, I can just separate with a plus between them. And anything that's in the denominator gets a minus in front of your log. Right? Gets a minus in front of your log. Of course, any exponents come out to the front. So in reality, if I think about this, and there are a few people sometimes that can't do this in one step, but many of us could have done all this in one step. So I'm going to write another one up here. And let's just see if we can do it in one step. Okay? So let's say we were doing, and I'm going to put a number in there, log with base 2 of 5x squared over 3y z. Okay, and we're trying to use our properties of logarithms to rewrite it in each expression where we have a single base. Well, I can automatically know that this is log with base 2 of 5 plus 2, bring that exponent down, log with base 2 of x, minus, because it's in the denominator, log with base 2 of 3, minus log with base 2 of y, minus log with base 2 of z. One step. Okay, so think about that. Let's think about that while we do this next one. Okay, first thing though, I never want a radical inside my logarithm because logarithms are exponents. Excuse me. So I want to see that log with base b as an exponent. X cubed y to the 5th z to the m, all to the 1 over n. Okay, so now let's get rid of those parentheses so it looks like this, right? And let's make it log with base b. Remember, if you have an exponent raised to an exponent, you multiply. So this would be x to the 3 over n, right? 1/3 times, not 1/3, that's not 1/3. 3 over 1. 3 over 1. This is 3 over 1 times 1 over n, right? Multiply straight across. Times y to the 5 over n times z to the m over n. Now let's see if we can do it in one step. Okay? 3 over n log with base b of x plus, because it's in the numerator, 5 over n log with base b of y minus, because it's in the denominator, m over n log with base b of z. And I have 1x, 1y, 1z as individual arguments. Okay, so practice those properties. We're going to need them next time. Okay, and in particular, next time, this is what we're going to do mainly. We can use them in the opposite direction too. And if I have a bunch of logarithms that spread out, I can condense them down into one logarithm, which is the main thing we want to be able to do. Okay, notice first of all, we got to double check. They got to all have the same base. So my goal is I'm going to write this as log with base 3 of just one thing. Anything that's positive goes in the numerator, right? So I'm going to rewrite it like this. Anything that has a minus in front goes in the denominator. Simple as that, right? If it's positive, it goes in the numerator. If it's negative, it goes in the denominator. If there's a numeral in front, it comes up as an exponent. So this is going to be written as log with base A of one argument, not one single letter or number, but one argument. Instead, I've got an argument here and an argument here. Positive ones go in the numerator, so that's an m squared. Negative ones go in the denominator, so that's an n cubed, because that has to come in. Okay, make sure these all have the same base, so they are all base B. Okay, positive, positive, and a negative. So bring the 1/2 in, so we have m to the 1/2 in the numerator, and bring the 3/2 in. Now careful, because that whole 2 in gets the 3/2, right? And then the denominator, bring the square in, and once again, careful, that whole m squared in gets that. Now, on this one, once I bring this in, hey, I've got some simplifying I could do, right? We didn't have that up here, right? There was nothing to reduce, but if I've got m's and n's in the numerator and denominator, I got to work on simplifying that. So let's see what we have. This is log m to the 1/2 n to the let's make that, I forgot my 2 in there. So 2 to the 3/2 n to the 3/2, right? And then m to the 4th n squared. Okay, so these m's, right, can simplify. Remember what we would do? We'd have 1/2 minus 4. 1/2 minus 4 is negative 3.5, right? So, log, do not forget your base. All right, so I'm going to go up here. Remember, we have 1/2 minus 4, which I know is negative 3.5. Or I could either change that negative 3.5 to an improper fraction, or I might choose to do my math this way. Either way, I'm going to get negative 7/2, right? So whatever you need. So this is m to the negative 7/2. Now eventually we know we're going to have to move that down here. If you want to go ahead and put it down there and make it positive 7/2, because negative exponents, we can't leave negative exponents ever, right? The 2 to the 3/2 is going to stay, because I don't have another base of 2. And then this is 3/2, or 1.5 minus 2. This is negative 1/2. Again, however you want to get that, right? 3/2 minus 4/2. Or just think, oh, this is 1.5 minus 2, so I'm going to have a negative 1/2. Okay, so for final answer, let's do final answer like this, just so we don't get lost, equals log with base B, right, 2 to the 3/2. And negative exponents means they have to come down here, m to the negative 7/2, so we can write them as positive. So that was just simplifying a fraction, right, using our exponent rules. Okay, get well practiced about going this direction. Okay, here's a big giant caution to end on. There is no property of logarithms to rewrite a logarithm of a sum or a difference. So notice in that previous example, we had one that said log with base 3 of x plus 2. No, you don't spread that out. No, no, can't do that, right? It's when your arguments are being multiplied that you spread it out with a plus sign. Just like exponents. If you had a to the x plus a to the y, we don't have a property for that, right? We don't have a property for that. Okay, so be careful about that. Also, the abbreviation log is a function name, not a factor. So we also see people a lot of times, you know, well, in the next section, if we have log with base 3 of x over log with base 3 of y, they want to try to cancel out that and just leave x over y. Nope, nope, nope. That's a function name. It's like, it's, you know, serves the property of f of x. It's not anything. It's not a numeral that we can do that with. So be careful about those two items. All right, I'll see you next time. Let me know if you need anything.